This is the view of the operation of these cornering lights from the outside of the vehicle, with turning left, right, but using the opposite turn signal indicator. And when moving backward. And all this code is available on this channel's GitHub page, the link to which is in the description under this video. So, what I've got here are 5 files. I should have made them CPP files, but Arduino was giving me some error messages, so I left them as header files. So in this all project, I have sub-projects. The files we have are the main file, which I call drivers Pico MC. It is the main project file in which our program begins and runs, and MC stands for multi-core. The second file is called canbusreader, which has all the necessary data and functions related to obtaining our vehicle's CAN bus data. And then we have corneringlights and canreader PIO. That is our actual canreader sub-project file, with functions to control our canreader based on the data provided by the code from the canbusreader file. And the last file that is not ready yet is servo control. After this project, I will make a short video about this sub-project as well. So please subscribe to this channel if you like to follow the development of this drivers Pico project in general. So, in our main file, we include the other 3 files, and also we define a variable called debug and set it to false by default. And this variable takes advantage of the Pico's onboard Neopixel. That Neopixel can be set to any color, which would help us with debugging and fault finding. So, if the bug is false, then the Neopixel will not be on at all. But if it is set to true, then as currently defined, the Neopixel will have red light if our right cornering lights has to be on, will have green light when our left cornering light is to be on, it will be yellow when our steering wheel is within the center range, it will be purple when we are going backward, and so on. The next 3 variables that I created are to be used with the Arduino's midis function. Then we have setup and loop functions for the first CPU core. As you can see, that core will be reading our CAN bus and acquiring the frames data that we need, and basically nothing else. Then we have the setup1 and loop1 functions, and these will be setting up and running our servo if it is the daytime, because I wouldn't record anything during the dark hours, and it will be running our cornering lights if it's the nighttime. And the same core will be running our Neopixel if the debug is set to true. And as you may notice, in normal operation, this code is basically running only either servo or the cornering lights. And that means that we will try to keep our Pico as efficient as possible. In the first core, we set up and read the CAN bus. Both functions are in our canbusreader file, where we include standard Adafruit RP2040 header file, define our CAN bus pin, create MCP object to get the CAN bus IDs and values, and then we define our baud rates, CAN bus speeds. After that, we declare the set of variables that relate to the CAN bus frames that we need to process. Which means, to obtain the light sensor data, we need light sensor frame ID, light sensor max value that I set here to 199, and this is because my real-world tests shown that the light sensor data in this car never goes beyond 200. And we also need to remember the last value given by this sensor, in particular if it's daytime or nighttime. And this brings us to a very important point, that CAN bus is an event-driven system, which means that the frames or messages are not put onto the CAN bus all the time, but instead are put there or sent down the bus when some event occurs, which means when this or that sensor's values change. Which means that here we need to have some specific variables that would remember the last values that we got when the frame was last on the CAN bus. Because that frame or the frame with that ID may never show up on the bus for even hours. Like for example with the light switch, if we don't move light switch, the CAN bus frame with that ID may not be generated for a long time. Then I define the variables that relate to the headlights frames. The headlight frame ID, the headlights data max value, and the current state of the headlights, where it is set to N for none, and can also be set to S for side lights, L for low beam, and A for auto. Then we have the variables that relate to messages with the vehicle speed. Speed frame ID, current speed, and the vehicle's direction. We also have variables for the turn signal indicator, that are turn signal CAN message ID, value for if we are signaling left, value when we are signaling right, and we need to remember the last state of the turn indicator, which is by default we set to N for none, and can also be set to L for left or R for right. And the last set of variables relates to the steering ankle, which is steering ankle frame ID and the steering ankle last value, which we here set to 4096, that is the steering wheel center position. Then we declare 4 functions that will be processing the frame data. After which goes our setup function that is called from the Arduino's setup function, in which we initialize our MCP object with the canB baud rate, which we declared in the beginning of our file. Our Pico is connected to the CAN bus B, so here we are passing the rate of 125 kbps. And after the setup function, we have the function called readCAN that is scanning our CAN bus all the time, in which we defined 4 temporary variables. One to hold the current frame ID, which we need to compare or test against the frame IDs that we need. Then the variable A that will have the first leftmost byte of the frame data, and the variable AA that will hold the second leftmost data byte. Even though our CAN frame data has 8 bytes, we here need only 2 leftmost bytes, because as you saw in the first video, for all the frames that we are actually interested in this project so far, we need the data from only the 2 leftmost bytes. So there is no point to waste Pico's resources on acquiring the data that we do not actually need. If in the future I would need some data from the frame that is in the 3rd or further bytes, then here I would add another variable like AAA or AAAA and so on. So if we look at the variables that we have here, then they look like this: frame ID, first leftmost byte of the data, and the second leftmost byte of the data. Then we also have a variable called packet size that would get the size of the frame that is returned by the MCP parse packet function. And if the returned value is more than 0 in size, we can get that frame's ID, and to get the frame's data, we are calling the MCP read function. Every call to this function gets 1 byte, beginning from left and going to right. But if the frame data is empty, then we are getting out of this readCan function and loop through the bus again to examine the next frame, and so on. If we have the full frame, then we can check if its ID is the one we need. And if the frame has the steering ankle, we then combine our steering ankle value variable that is 2 bytes long with the values from the first and the second leftmost bytes of the frame data. We are doing this by shifting the bits, meaning we move the first data byte into the first byte of our steering ankle val, and the second data byte we move into the second byte of our steering ankle val variable, after which our steering ankle val variable will contain the current steering ankle value. And so this is how I get the steering ankle value. Now, if the frame is not the steering ankle frame, then we can check if that frame has our light sensor's data. And if it does, then we are calling the function readLightSensor, which will simply compare the value of the first leftmost byte of the can frame, and if that value is less than our max light sensor value, then we will set or remember that it is the daytime. If not, then we have to remember that it is the nighttime. Next, as I said in the first video, I am not using the state of the headlights, so I commented out all this code and left it in case I need it for my future sub-projects. And then I have just empty else statement. After which we are checking, or better said looking, for the speed frames and for the turn signal frames only and only if it's the night time. This is because they directly relate to the operation of our cornering lights that we don't need if it's not the night time. And if it's the night time, then we test the current frame ID to see if it's the speed frame. And if it is, then we are calling the readSpeed function, which takes both leftmost frame data bytes. As you see, I put the command here to explain how the data in this frame is organized and how we are getting that data. This function needs to give us both the direction of travel and the current speed. What we are doing here is we are simply assigning the speed direction variable the first 4 bits from byte 1 by moving byte 1 bits 4 places to the right. And that means that our speed direction variable will have only the first 4 bits of the byte 1 variable. The other leftmost bits will be filled with zeros. Now, this function will also give us the current speed. To get that speed, we need to read the data from the 4 rightmost bits from the first byte, and then we need the full second byte, after which our current speed variable needs to be multiplied by 0.0375. That will give us values in mph. And if we want the values in kmh, then we have to multiply it by 1.609. Now we go back, and if that frame is not the speed frame, but it is the turn signal indicator frame, then we are calling function here readTurnSignal, and we are passing it the first byte. And this function simply tests if the first byte value is the same as turn signal left value. If it is, we are setting our turn signal variable to left. Else if the first byte contains the value 144, then we are setting our turn signal variable to R, meaning that we are indicating to the right. And else, by default, we are setting our turn signal variable to none. So we got our turn signal, then we come to the end of this function, and we get out of this readCan function back to main in the first call. Then we wait 10 milliseconds, and then we read the can again. So we repeat this code again. Now in the end of this canreader code, I put the comments. I will uncomment just. These are my own calculations relating to the steering ankle sensor, how to find, and all the other values. So this is how we get the CAN bus data that we need. This is all done in the first core. Then in the second core, we first do setup. This is our second core setup function. So that will set up server and will set up corneringlights. And if the bug is true, we'll set up our Neopixels. And in the loop, as said before, we will be running either Move GoPro, or if we have nighttime, we'll be running corneringlights. And the corneringlights functions are in this file. So we go through this file from the very beginning. So in this file, first of all, I am defining two major variables. Offset degrees, which relates to the degrees of our steering wheel, in particular how many degrees from the center, either to the left or to the right, it should be when our corneringlights have to be on. And I put it here in degrees, so it's easier for us to set the values. And then I define the max speed, after which our corneringlights will be disabled. Then we have standard Adafruit Neopixel header file included. Then Hardware PIO header standard file. And then we include our corneringlights PIO header file. This file relates to the state machines of the programmable input-output of the RP2040 processor. So, and this file is generated by the program called PIO ISM. And I have that program, and I have that executable file, PIO ISM, in my projects folder. So how do we generate this file? We go to our project. So in our project, we create the file called program corneringlights. This is the assembly file, and the assembly code is all these 4 lines here. All the rest is the helper for this PIO ASM file to generate the header file. So basically, this is the assembly code, which is basically a loop. Its first command sets the pin that we need to low, and then it sets the pin that we need to high, and then jumps back to the loop and repeats again. That's all it does. This is very similar to the blink example. All this is a standard routine. The only change you have to do is to change the program name. Here I have corneringlights and corneringlights, 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 and so on. We then need PIO ASM file. We go to our Arduino 15 folder in Linux, and I think this folder in Windows should be in your program files, not the user files, but in the program files. Then we go inside, we go to packages, we go to RP2040, then we go to tools, and then we have PQT PIO ASM folder. Inside there we have PIO ASM. We can copy and then move it to our project files and paste it here. And then what we do, we open our console, we type PIO ASM, then we give it first parameter as our assembly file as corneringlights.pio, and then we define the output file that I can simply say out.pio.header, and as you see, it will generate us this file. So this is how we get our corneringlights PIO header file. If we look inside this file, we can see that those assembly instructions that we generated are here, and all the functions. So after that, after the include, we create an object called Neopixels. This is the standard for onboard Neopixel. Then here I define variables for setting up the colors for our Neopixel, what we need here, in case we need any. Then if you do not have the RP2040 CPU, or if you don't want to use any PIOs, just to use normal switching on and off of the relays, then you uncomment these two lines. As you see, we control left relay from pin 1 and the right relay from pin 25. So you uncomment these two lines, then you have to comment all these or just delete them. These 4 lines relate to our PIOs, to enabling our Pico to use state machines. We are creating PIO object with the PIO 0, and in this project we can have PIO 0 or PIO 1, 2 programmable inputs, outputs. Then we create offset variable, that is the offset for the location of our assembly program in the CPU's memory. Then we create 2 state machine variables, left and right. Then these 2 variables relate to the Arduino's MIDIs function. I need them to delay, to switch off and on the cornering lights. Our setup cornering lights function is called from the main setup1 function. And in this function we assign the values to our offset1 variable that will hold the memory offset in the PIO 0 for our cornering lights assembly code. Then our smLeft variable is assigned the free available state machine. That state machine will be running our cornering lights assembly routine to switch on or off our left cornering light. Then we initialize this cornering lights routine in the smLeft state machine that will be attached and will be controlling the state of the pin 1. Then we do the same with our smRight state machine and attach it to the pin 25. And here is where we attach our assembly code to run inside one of the state machines on a specific pin. And if you don't use PIO, you have to comment all of the above and uncomment these 2 lines that are setting our pin 1 and pin 25 as the output pins. And in the following 2 lines, we actually invoke our assembly code, and 0 means the pin 1 and pin 25 are set to low. In other words, they are switched off. If you don't use the PIO, then you control these pins via digital write function, where we set our pins to low for off and high for on. And in the end of this function, we set the current pixel color to yellow. Then we have 3 more variables that will hold our steering center value, steering offset to compare against the steering ankle value received from the CAN bus, to which we assign the value that we set on the top of this file and multiply it by 2. So that we can later test this against our current steering ankle. And we create the variable that will remember which cornering light has to be switched on. And we set its default value to n for none. And this variable is assigned the value inside the check steering ankle function, to which we will come a bit later. And then we have 2 more functions, where we begin with a function called run cornering lights. This function is called from our loop1 function, and the first thing it does is checking if our current speed is below the maximum set speed that we set on the top of this file. And if the speed is too high, Then we don't do anything here and get out of this function back to the loop 1. And as you can see, in the loop 1, if it's nighttime, we are then calling this same function again and again and again. But if the speed is lower than our maximum speed, then we are calling check steering ankle function. That will compare if CAN bus steering ankle value is greater or smaller than our max steering ankle value. And it will set the value of the cornering light variable that will be pointing to which cornering light is to be on, or if none of the cornering lights should be on. After that, we wait 100 milliseconds and call the function switch cornering lights. And this function is doing the actual switching of the cornering lights on or off based on different conditions. So in this function, we are basically comparing the conditions. First condition is if the speed direction is greater than 4, which means that we are going backward. And here I said that if I am going backward, I want both cornering lights to be on to have max visibility around the car. So I'm switching the left cornering light on. As you see, we have one here now. And also switching the right cornering light on. And I am setting the current pixel color to purple. And the switching delay here I am setting to 4 seconds. This means that after going backward, our cornering lights will stay on for another 4 seconds. And of course, if you don't use the PIOs, then you have to uncomment this line and uncomment this line and comment these 2 lines. And after we've done this code, we go back. We go basically out of the switch cornering lights function and go out back from the run cornering lights function. We go back to our loop 1, and if it's still night time, then we run cornering lights function again. And let's assume that now we are no longer going backward, where we compare the current speed again. We look at the check steering ankle, and then the switch delay is now 4 seconds. That means we are waiting here 4 seconds, and we are calling this switch cornering lights function again and check the conditions. If we are not moving backward anymore, then we are checking if our left cornering light should be on. If not, then we are checking if our cornering light is set to right. If not, then we go to the default code, where we simply make sure that both are switched off. We set current pixel color to yellow, and then we set the switch delay to 100 milliseconds. And after that, we get out of this function. We go to the loop again. We go to this function again. And let's assume we are going forward with a speed of 10 kilometers an hour, and our steering ankle is well to the left. So we are checking the steering ankle, and if the steering ankle function decides that our cornering light now should be set to left, then we wait 100 milliseconds and call the function switch cornering lights. So in this function we check direction. If it's backward, is not. Then we check if the cornering light is set to left. It is set to left. Then we check if our indicator is set to right. If it's not, if we simply go in left, then we switch on the left cornering light and make sure the right cornering light is switched off. And if you don't have PIO, then you uncomment these 2 lines and comment these 2 lines. Then we set our current pixel color to green, meaning that our left cornering light should be on. Then we set the switching delay value to 2 seconds, which means if we return our steering wheel to center, our cornering light will be switched off 2 seconds later. So we came to end of this code, and that means we came to end of this function. We came back here. We record the current time from our millis function to remember. Then we get out to the loop 1. And then back from the loop to run canreader function, where we compare the speed. If speed is low enough, check the steering angle. Then we wait 2 seconds that we have just set. After 2 seconds, we call the switch canreader function, where we check if we are going backward, if the cornering light L is on, no. If cornering light R, right, is on, no. If none of the cornering light should be on, then we come to this default code, where we make sure both cornering lights are off. We set the current pixel color to yellow, and then switch delay will be set to 100. And this function repeats again, so let's assume that we are now indicating, let's assume that we are driving on the roundabout. We are driving left, our cornering light is set to left here, but we are exiting and we are signaling right. So we are calling this function. Then we check condition no. Here we are going left, yes. Then here we are indicating right, yes. That means that we are switching our cornering light from the left to right. That means that we are switching our right cornering light on and make sure our left cornering light is off. And then we set the switching delay to 1 second. So after we stopped signaling, we wait another second, and then we'll be running this function again. So this is basically all the cornering lights controlling code. All in this file, only 3 functions. One is called from the loop 1, which is second core. And if you have a single core, like for example if you have Arduino Uno, then you take all this code from loop 1 and move it to the function loop under the existing code there. And the same you have to do with the setup 1. So in setup 1, you take this code and move it below the setup and just leave 1 second delay. And I here have to mention one more thing, is that I consider this canreader project or sub-project ready for basically 99%. And I say so because in our read turn signal function in the canbusreader file, the values that I have for turn signal left and for turn signal right apply only when we are not actually switching the turn signal switch, but instead just touching it. A few years ago, I have programmed my vehicle with VDAMO to have 5 blinks instead of 3 when touching my turn indicator switch, because 99% of time I do not switch it, I only touch it, because the 5 blinks is always enough for me to indicate where I am going. And for this reason, when I was looking for turn signal values with the SavvyCan, as you saw in the first video, I did so by not switching the turn signal indicator, but instead only touching it, left and right. And I simply forgot to work out the values for this frame when the turn signal switch not just touched, but also switched on. And only recently I've noticed that I have this problem. So when I have time, I will try to connect my SavvyCan again and work out the values. And the file in the GitHub page will be updated, and if I do so, then I will make a comment on the new version when it is updated, so that we have the data values from the same frame when not just touching the indicator switch, but also when switching it on. But again, as I said, this function is used very rarely. We have to be on the roundabout basically. We have to go very slowly on that roundabout. Otherwise, this function is not invoked at all. So this is basically our corneringlights project. How it's done, how it's run, and how they work. In the next video, the third and the last part, I'll be covering the installation of the hardware itself, beginning with Pico, running the wires, relays, and installing the lights themselves.